Hi guys, today I'm going to be talking to you about adding libraries and multi-threading in C++. First of all, I'm just going to kick things off with a small recap on threads for people who are still a bit iffy on things. I hope this clears it up. What are threads? Threads are small independent chunks of code that can run concurrently with other threads in a program or in other programs. Each program has to have at least one thread, but a thread isn't necessarily a whole program. Multi-threading. Single-threaded programs are easy to run concurrently as the operating system gives each program a small amount of memory to run all their operations in and to keep track of their local variables. However, with multi-threading, things get a little bit more complex. Most of the time, the socket thread just sits there waiting for data to arrive and then sends it on to the main thread. This prevents the main thread from continually asking if data has arrived, stopping CPU cycle wastage and makes it more memory efficient. However, there are a few problems with this method. Since the data is being put into a buffer and then sent onto the main thread, if more data arrives at the socket thread and is sent on while the main thread is still revising the old data, it could override that data, meaning that the data is corrupted. Therefore, we need to implement mutexes. Mutex stands for mutual exclusion and is the most simple and useful form of synchronization that we can employ. If any of you guys remember critical sections from operating systems, this is essentially the same thing. It is essentially just a boolean that says whether a section of memory is locked or not, therefore telling the queue of threads if it can use it or if it has to wait for a thread to finish up. There is, however, a drawback. If a mutex isn't unlocked after the thread is done with it, any threads that are still waiting to use it will just be left hanging indefinitely, so the whole program will hang and become useless. Another problem is that if a thread has to do a lot of processing, or there are multiple threads that have to do a lot of processing, the program is going to run really slowly by having to wait for each thread to finish its calculations on that bit of memory before it can move on. So we use another form of synchronization called semaphores. Semaphores are objects that allow a certain number of threads access to a bit of memory before it puts all the other threads in the blocking state. A semaphore with a value of 2, for example, will allow the first 2 threads into the block of memory, then leave the other threads waiting until those 2 threads are done. A mutex is in essence a semaphore that only allows one thread in at a time, so it's not a completely alien way of doing things. Conditional objects. These are pretty simple and straightforward. They have 2 main commands, wait and signal. If there's a thread that does nothing until a certain event, then it's pretty memory efficient to have it just running in the background until that event occurs. An example that John gave in the notes is of enemy AI. If a player is not in a room where the enemies are, then what use is it for them to go about their routines? So instead, we just put them in a sleeping state until the player arrives, and then they can go back into being the bad guys or the backup or whatever they are. There are, however, some problems with multithreading. Each thread requires a chunk of memory, so each program is given a stack to work with to keep track of its local variable data, to run its functions, etc. Depending on the amount of functions being called, the operating system tries to give a big enough stack to the process so that there won't be any stack overflow exceptions, etc. We've all seen what can happen. When these threads, however, start getting more complex and doing a lot more things, it becomes clear that they need stacks as well. But not all threads do complex things, so giving every thread a very big stack is a severe waste of memory. So we have to find a way around that. So if you guys have any ideas or know how it's done, if you could just tell me, that'd be really helpful. On single processor systems, there's a lot of sort of more processor overhead involved, since there's only one processor that has to do all the calculations, rather than multiple cores dividing the load between them. So logically, the more threads and processors there are, the slower the computer runs. However, some things you can't get around, and if you need lots of input and output calls, that requires a threading, and there's no way around that. As I mentioned earlier, corruption could become a serious issue. If semaphores and mutexes aren't used correctly, the data that you're trying to transfer could become corrupted and useless. You should be absolutely certain at all times that the data is only modified when there is only one thread reading and writing to that bit of memory. This can be done with semaphores and mutexes, as I mentioned earlier. Problems with corruption, obviously, except for the data being corrupted, is that it can lead to unexplainable bugs and headaches later down the line, and there's really hard to track down, and you can't really debug corrupted data. Since most debuggers don't support multithreading, it becomes a bit of a hassle to debug these programs. Even the debuggers that do support multithreading have issues, since usually it just stops the one thread that you're debugging but allows the others to continue running as normal. And this isn't how it works in the real world, so it becomes a bit useless if you're trying to find a bug that has to do with all the threads currently running or passing information from one another. Another problem is that multi-threaded programs are non-deterministic, which means the operating system chooses which thread runs when. So that means that the programmer has absolutely no control and could make an absolute nightmare trying to find any bugs to do with that. Most operating systems have built-in multi-threading libraries. However, unlike the sockets that we did last week, these libraries aren't all compatible, meaning you have to choose which library you want to use, depending on the operating system that you have on the machine. Windows has a built-in threading library, which makes things very handy. However, Linux depends on pthreads for its multi-threading library. What the threading library allows us to do is to create threads, kill threads, wait for threads to finish, get thread IDs so we can select threads and use only the ones that we want to. It yields threads to the operating system, and it is all encompassed by the threadlib namespace. Doesn't matter which operating system. Headers and type diffs. Depending on what the compiler is you are using, you have to either include the windows.h or pthreads.h header files to use with your program, depending on the operating system, as I mentioned earlier. Typedef void star threadfunc and star void defines a function pointer type that returns nothing and takes a void parameter as argument. As you might remember, star void means that you could pass any parameter in, and we use this in a couple of different ways later on, as I'll talk about it. Whenever a thread is created, it also creates a function. This typedef describes what kinds of functions can be executed as new threads. As I mentioned earlier, the void star parameter allows for the passing in of any object as a parameter to the function. This is super useful as it allows us to have a pointer to a number, a class, a collection class that we made, a character as we use later, or any data type that we want to pass in. The thread ID typedef class allows us to reference any threads we want to kill or wait for or finish that we have created earlier. Linux uses a single data type to reference it, while Windows needs a thread ID and a handle to reference the object, which seems a bit needlessly complex, but there you go. When we create a new thread, it needs a function pointer to execute in the thread. The 132 threading library makes it look like this. The second line from down, you can see dword WinAPI function void star. This means that it returns a dword, the WinAPI calling style, and takes void star as a parameter. pthread requires a function to look like void star function and then void star as a parameter. It returns a void star, it has no function calling style, and takes in a single void star as its parameter. The thread function typedef is almost the same as the pthread star, except it has no return value. I believe the dummy function passes the parameters and thread ID to the main function, irrespective of what operating system it's running on. But if that's wrong, could you guys just let me know, or if it's used for something else, that'd be really helpful. So whenever you want to create a thread, you have to pass in both the function that you wish to execute and the parameters. In turn, the function passed into the dummy data structure is handed to a dummy function, which then executes the function that you want to call in the first place. The dummy thread function needs to know two things. Firstly, it needs to know the function that the dummy thread needs to call, and secondly, it needs to know the data that it's supposed to pass into the function. The dummy function can only take a single void star as a parameter. As a result, you need to package the dummy thread into a collection class of its own. Now we'll take a quick look at the code. First up is the threadlib.h header file. As you can see here, includes the three header files that we use as well. This keeps things nice and tidy and makes coding a lot easier. The threadlib functions.h file is used to create, kill, and make functions wait. As you can see here, we include the thread libraries for both Windows and for Linux. Here we define the standard thread function format, which takes void star as a parameter and returns void. Here we define the thread ID data type depending on the operating system. For Windows, we include a dword and a thread ID, but with Linux, we just need the thread ID, keeping things pretty simple there. Here we have the dummy data structure that takes in the name of the function and the data. Here we have the dummy thread function. It takes in a void star pdata parameter, the same for Linux, though with Windows we need to add the dword as well. Here we have the thread ID create function. This creates a thread and returns a new thread ID, and its parameters are the thread function and the p-param. The function will create a new thread and will execute the p function with p-param as its argument. Here it creates a new dummy data block with the function and the parameter. Here it creates the new thread. The null you see here is a security attribute, but we don't use it, so we just leave it as null. This is the initial stack size, but we just leave that at 0 so that the operating can resize it automatically and decide how big it should be. Here, this is a pointer to dummy run, and this is a pointer to dummy data. This is for the flags. I'm not sure what the flags are, but we don't use them, so we leave that as a 0. And this is the thread ID type. Here we pass the handle into the handle map. This, of course, is used only for Windows, and on the Linux side, things are almost exactly the same. We just take in the thread ID type, set the initial stack size to 0, and reference dummy run and the data type. Here we get the current threads, pretty simple in both. We just call the current thread ID or the pthreads underscore shelf. Here we wait for it to finish. We look up the handle and wait for the thread to finish. We close the handle to the thread that has just finished, and we remove the handle for the handle map for Windows. With Linux, it's just pthread join. Here we kill the thread forcefully. This terminates the thread. It's not really advisable unless it's absolutely necessary, so I don't know if that's just for graceful exit or if it causes a memory leak. But here we terminate the thread, we close the handle of the thread, and remove the handle from the handle map. With Linux, it's just pthread underscore cancel. This function allows the thread to sleep. As you can see here, we sleep and we set it to milliseconds. And here we have to unsleep and milliseconds times 100 since Linux decided to use microseconds. Here we have the thread exceptions header class. It's mostly uninteresting, just checks for any errors that occur and sends them on. Here we insert the error code for the exception with a default value that we leave unspecified. Not entirely sure how a lot of this works, so if anyone wants to elaborate, that would be fantastic. Now onto the threadlib mutex header file. As you can see here, it's all pretty straightforward. Here we initialize the critical section for both Windows and Linux. Here we delete the critical section. This is where we lock the critical section when a thread enters it, and we unlock it after the thread exits. Otherwise, it could cause the system to hang. Sorry, but I'm running out of time on this recording, so I'm just going to start another video, and next we'll be looking at threadlib.cpp.